When we calculate equilibrium constants, we put the numbers into the equation, we solve it, and we get the answer. So in this case, we would take 0.166, and because there's two NH3s, we would square it, over N2, so that's 2.46, times H2 7.38, and because there's three of them, it would be cubed. And then we take 0.166 squared divided by 2.46 divided by 7.38 raised to the power of 3, and we get 2.8 times 10 to the minus 5th. Okay? Now, those are pretty easy ones. You plug the numbers in, you get the answer. Sometimes they're not as easy. Okay? For example, sometimes they give you the equilibrium concentration, or they give you the KEQ, and you have to find some of these values instead. So when you do this, we're going to make what's called an ICE table. And ICE stands for initial, change, and equilibrium. And then we're going to put everything in to that ICE table that we can, and then we're going to try to fill out the rest of it. Okay, let me show you how this works. So example 1 says, enough ammonia is dissolved in 5 liters of water to produce a solution that's initially 0.0124 molar in ammonia. The solution is then allowed to come to equilibrium based on the reaction below. Analysis of the equilibrium mixture shows that the concentration of hydroxide is 4.64 times 10 to the minus 4th, and they want us to calculate the equilibrium constant. So, in this case, what we're going to do, right below the reaction, I'm going to make a table. Okay, and that table is going to have 3 spaces, I, C, E. And then I'm going to make a spot for all of them. Now, the first thing I'm going to do is I'm going to remember I stands for initial, C stands for change, and E stands for equilibrium. And then I'm going to go back to the problem and I'm going to read. Okay, and I'm going to read that it says initially it's 0.0124 molar in ammonia. Okay, and ammonia is NH3. I probably should have said that in the problem. Okay, so ammonia is NH3, so that means initially, remember I is initial, it's 0.0124. Okay, and then I keep reading. The solution then comes to equilibrium, so now we're down here at equilibrium. Analysis of the equilibrium mixture shows that the concentration of hydroxide is 4.64 times 10 to the minus 4th. So the concentration of hydroxide, which is OH minus, is 4.64 times 10 to the minus 4th. That means right here, we're going to put 4.64 times 10 to the minus 4th. Now, that's it. That's all that they tell us. And supposedly, that's enough information for us to be able to fill out the rest of that box. All the rest of these squares. And it is. And I'll show you how. So first of all, remember that when we write an equilibrium constant expression, we do not include solids or liquids. And right here we have a liquid. Which means, what are we going to do with those boxes? Nothing. We're going to cross them out. Anytime you have a solid or a liquid in an equilibrium system, you can just cancel that part out. Okay, the next part is initially, they said initially we started with 0.0124 molar ammonia. That also means that initially there wasn't any NH4 plus, there wasn't any of this, and there wasn't any of this. Which means if there wasn't any of it, how much did we have initially? 0. 0 and 0. We didn't have any product to start. And that's very common with equilibrium, is you start with a reactant. And then, again, initially there are no products there. Now, notice right here we have the initial and we have the equilibrium. If we have those two, now we can figure out the change. Because if initially it was 0 and now it's 4.64 times 10 to the minus 4th, guess what? That means that OH minus went up by, notice the plus, it went up by 4.64 times 10 to the minus 4th. Okay, so this number here is just the difference between those two values. Okay, so between initial and equilibrium, it went up by 4.64 times 10 to the minus 4th. Now, here's the tricky part, is this change part, the C, is where we have to use what the stoichiometry of this equation. Notice that, and what I mean by that is notice that for every one hydroxide that gets produced, you also get one NH4 plus that gets produced. So no matter what, if we get 5 OH minuses, you're going to get 5 NH4 pluses. If you get 150 OH minuses, you're going to get 150 NH4 pluses. If OH minus goes up by 4.64 times 10 to the minus fourth, then so does NH4 plus. Because again, based on the stoichiometry of the balanced equation, for every one of these that's made, one of these is also made. So the change for them is going to be the same. Well, what if it was a 2, Mr. Johnson? What if instead of a 1 here, there was a 2 right there? Well, then in that case, then it would be double that amount. Okay? Because for every one of these, you would get 2 of these. So you would have to double this 4.64 times 10 to the minus fourth. Okay, let's keep going here then. Now notice, and there isn't actually a 2 there. Notice that NH3 also is a 1 as well. And if the products go up by that amount, then the reactants are going to go down by that amount. Okay? And now we're almost done. Okay, so this, remember, was 0. This went up by 4.64 times 10 to the minus fourth. So equilibrium, they are the same. And then for the equilibrium for NH3, I'm going to take 0.0124 and I'm going to subtract, remember, because it went down by that amount, 4.64 times 10 to the minus fourth. And I get roughly 1.19 times 10 to the minus second. Okay? And now I can put those numbers. Once I have my equilibrium values, now I can put those numbers into the equilibrium constant expression. So Kc is going to equal the concentration of NH4 plus times the concentration of OH minus, same number, 4.64 times 10 to the minus fourth, over the concentration of NH3, 1.19 times 10 to the minus second. So now I just go to my calculator. 4.64 times 10 to the minus fourth times itself divided by 1.19 times 10 to the minus second equals 1.81 times 10 to the minus fifth. Okay, and that is our final answer. All right, let's look at another example here, example 2. Okay, and this would be a good point right now to go ahead and stop, pause the video, and go ahead and try to do this yourself. Okay, and if you can do this yourself, then just walk through your answer with me and see if we get the same answer. If we don't, then check and see what you did wrong. But there's example 2, and then there's also example 3 that we're going to do. So if you want to stop right now and just see how far you can get, see how much of this you can do without me doing it for you. Okay, and it's a good time to take a break anyway. So, sulfur trioxide, SO3 gas, decomposes at a high temperature in a sealed container producing SO2 and O2. Okay, so first of all, we need to write the balanced equation. So SO3, it says decomposes, okay, and then it's going to form an equilibrium. It says at equilibrium, and it's going to produce sulfur dioxide, SO2, and oxygen gas, O2. Okay, so first of all, we need to balance this equation. So we've got 3 oxygens and 4 oxygens, so we're going to have to double this side, which now makes 2 sulfurs. So we're good there. So now the equation is balanced. So now we're going to go ahead and make our ice table. And by the way, sometimes people call these rice tables, where R stands for the reaction. The reaction goes up here. I don't like that though. I like ice better. Okay, either way, rice, ice, who cares? Okay, now let's start putting in our numbers. So initially the vessel is filled at 1,000 Kelvin with SO3 at a pressure of 0.5 atmospheres. So that means 0.500 atmospheres. And again, if initially it was only SO3, how much SO2 and O2 do we have? None. And then at equilibrium, the SO3 partial pressure is 0.2. So that means this is 0.2, right? At equilibrium, SO3 is 0.2. So now we have enough, because if we know the initial and we know the equilibrium, we can figure out the change. How much did SO3 change from the initially to equilibrium? Well, it was 0.5 and now it's 0.2, so it went down by 0.3. Now again, here's where you have to use the balanced equation. It's a 2 to 2 ratio. So if SO3 goes down by 0.3, then SO2, because it's the same ratio, is going to go up by that same number. Okay, but then for O2, notice it's a 2 to 1 ratio. So it's only going to go up by half as much, because for every 2 of these that get used up, you only get 1 O2. So it's only going to go up by 0.150. Okay, and then 0 plus those equals that. And now we have our equilibrium values. So Kp is going to equal the pressure of SO2, which is 0.300, and that has to be squared, times the pressure of O2, 0.150, over the pressure of SO3, which is 0.200. And again, because of the 2, it's also squared. So I get 0.300 squared times 0.150 divided by 0.200 squared equals 0.3375. I'm just going to round that to 0.338. Okay, and that is our final answer there. All right, last one. Okay, acetic acid, a weak acid, creates an equilibrium system. Calculate the hydrogen ion concentration in a 0.125 molar solution of that acid. So here they're giving us the equilibrium constant, and they want us to find the hydrogen ion concentration. Oh boy. Okay, so first of all, let's write the equation again so we can make our ice table. And here's where it gets a little bit more fun. Okay, so here's our table. Boom, boom, ICE. All right. So all that they tell us, we get one thing. It's a 0.125 molar solution of the acid. So that's 0.125. That's it. That's all that they tell us. Well, if it's 0.125 molar of the acid initially, that means, again, that there's no H plus and there's no acetate ion. Now, the fun part is here. We don't know how much they're going to change, but we know that there's a relationship based on the stoichiometry of the balanced equation. So we know that that acid, we know that here it's going to go down by a certain amount. We just don't know by how much. So what do you do in math when you know it's going to change by a certain number, but you don't know what number it is? What do you use? You use the letter X. So here I'm going to say this is going to go down by X. Okay, and then because it's a 1 to 1 to 1 ratio, that means this is going to go up by X, and this is also going to go up by X. So at equilibrium, we have X, and we have 0.125 minus X. Now we have to solve this. Now, if you're kind of jumping ahead here, you're going to realize on the top, you're going to have X times X, which is X squared. On the bottom, we have 0.125 minus X, and that's going to equal the equilibrium constant, 1.8 times 10 to the minus fifth. Now, if you kind of jump a little bit ahead in your brain, you're going to realize that we're going to reach a point where the only way to solve this problem is to use that dreaded quadratic equation, or the quadratic formula. Negative b plus or minus the square root of b squared minus 4ac over 2a, right? Okay, I'm telling you right now, you will never ever have to use the quadratic equation in my class, whether it's regular chemistry, honors chemistry, advanced chemistry, AP chemistry, it doesn't matter. I will never ever make you use the quadratic equation. Because, and here's why. Because this X value, we don't know what it's going to be exactly, but we know that it's going to be a pretty small number. Okay, and in terms of I want to make the math easier for you, and I never want you to do the quadratic equation, we're going to make an assumption here that 0.125 minus x, watch my equal sign here, is going to be roughly equal to, still really close to 0.125, because that x value, and again, this isn't me making up this rule, this is what they use in chemistry. And they say, you know what, just to remove the quadratic equation, here's what we're going to do. We're going to take that minus x, and we're just going to get rid of it. Okay, and what that does is it makes the math way, way easier. Because now to solve for x, I just need to multiply this side by 0.125. So that's what I'm going to do. I'm going to take 1.8 times 10 to the minus fifth, and I'm going to multiply it by 0.125. And I get 2.25 times 10 to the minus sixth. And I don't really care what that is, because that's x squared. X squared equals 2.25 times 10 to the minus 6. Because now I don't want x, I don't want x squared, excuse me, I want x. And so now the only thing I have to do is I have to square root that answer. So now I'm just going to hit square root that answer, and I get my final answer of 1.5 times 10 to the minus third. Okay, and if you notice that, that's a pretty small number. Okay, x equals 0.0015, which means that if we had actually subtracted this, this still would have been like 0.124. Still really, really close to 0.125. And so our answer is close enough that we can say, yeah, let's just get rid of that minus x on the bottom by making this assumption here. Okay, because the answer is 1.5 times 10 to the minus third. That's the hydrogen ion concentration, and that's what they're asking us for in this question. Okay, and guys, that's as difficult as it's going to get right there, is when they give you the equilibrium constant and you have to solve for one of these products by using x's. Again, the more you practice it, the easier it's going to be. And so again, I'm going to give you some more problems with this for your homework to practice this more and more.